Welcome to the Society of Amateur Radio Astronomers Radio Telescope Observation Party. Today the observer, Richard Russel, will describe how he uses his 9-foot dish with a 1420 megahertz feed to measure hydrogen Doppler and using this data, determine the velocity of the sun around the galaxy and the mass of the galaxy. He starts with his real-time measurements with the team.
On really the goal here is how do you set up, how do you look at hydrogen data, and you guys could actually do this with your SDRs because the data is very similar to how the SpectraCyber outputs the data. It's just a single file per scan, and then you get a level, and then you just have to adjust it to the frequency and then plot it. So this is very similar, and the next thing I will do is eventually is plug my 9-foot dish into an SDR exactly the way the scope in the box SDR, and then take data and see what the difference is between the small antenna and the 9-foot dish with all the gain I put on it. So anyway, that's what it looks like. Now, give you an overview of how this looks. On the top, there is a let me get my pointer. On the top here, I labeled it Deck 44. So I've got to set up declination 44. My goal here is I'm going to show you how to calculate the rotation rate of the galaxy and the mass of the galaxy. So declination 44 is where the galactic longitude of 85 degrees is. So the goal here is to get galactic longitude 85 degrees and galactic latitude at 0. And so that's actually the bottom number is the first is the date in UTC time, but the second part I've got it set up for sidereal time. And since I'm pointing north at this time on the meridian, that is right ascension. So right now, what you're seeing is right ascension of 12 hours, 52 minutes, declination 44. And then I'm drift scanning, so basically the time is it's just scanning the sky as we rotate. And I'm recording it also, so I can actually play this thing back on the recording. So you can actually see in high speed where the signals come up and down. And did that last night, and I got a lot of found out I do have a lot of RFI at certain times of the day. Doesn't appear so now. That's the variability you see on the front end is just a variability. It's just different scan noise, but that signal right there that you see pop up is the hydrogen at this location. So I'm in Colorado. So if anybody, so everybody know Colorado Springs, that's where the dish is. Any questions on this before I shift to sort of the presentation mode and show you how to set this up, etc.
So there's a SpectraCyber program, and that runs on Windows, talking to serial connection?
Yes, it's a USB to serial. In fact, the reason I have it on an old computer was that it has to talk to COM 1 or COM 2 port, and that this old computer made it really easy to do, but the new Windows and the new computers don't. There's a legacy to set up COM 1 and COM 2 on your new computers, but I haven't set it up on this new computer yet. So I've got it set up on my old computer, right? But that works just fine. And it's already set up for the COM. I think it's COM 2 I got to set up on.
Have you tried running a Raspberry Pi?
Well, the software will run on any Windows software, as far as I know. And I'm just saying, it just takes it'll take the back of the SpectraCyber has a RS-232 serial port that's expecting COM 1 or COM 2. All right, so as long as you can output And I have this little serial adapter that goes from USB to serial. You need one of those, and then you plug it in, and then you have to set up your COM1 or COM2 port on your computer. Should run, or on your Raspberry Pi. Should run. Okay, so the goal here is show you guys how collect hydrogen data, at least the way I've been collecting it. And trust me, I'm a very newbie at this. I've been doing it for 2 years since I've actually got a SpectraCyber, which is part of the Deep Space Exploration Societies. They own it. I've basically set it up, but I did manage to get a free 9-foot dish, and I got Ray Uberekin from the DSES organization built a great hydrogen feed, and then we put about 60 dB of preamps on it. So I've got almost too much signal, and then we got plugged that into SpectraCyber, and it ran almost immediately. So the only issue is, how do you set it up, and how do you get the data back, and things like that. But one thing that I believe highly in is that collecting data is one thing, but unless you have something to do with it, then you're not. You should be wanting to. You should be using the data for something. 1 second. Trying to get my video back online here. There we go. Okay. Not that you guys wanted to see me, but here I am. All right, going back to this. All right, so the goal here is that show you how to get the data, show you how to calculate, or basically figure out the how they figure out the velocity using the data, using the Doppler effect. And then from that data, you can actually calculate the mass of the galaxy. Sorry, I'm trying to admit people here while we're doing the video here, so stand by. All right. Okay. All right, so here's the dish. And a 9-foot dish, my backyard. There's the feed. So it's a center feed, and it does have two 30 dB preamps in series on there. The focus distance, here's the calculation for that. So the one thing and you can see the interior, it's set up for a 2 polarizations. That's what you see on the left, what these two polarizations here are. But I'm only using one. I think that it'd be very, very nice to have 2 coming in, but right now I only got 1 receiver. But if we got 2 SDRs, maybe get 2 SDRs and combine the data, would be interesting. And it's very important here, especially with this kind of a feed, is where is the bottom? The distance here is really the bottom of this can here to the dish is what you're talking about. And there's the formula for focus distance. And so we measure 22 inches. That's from the flat end. If you basically put a tape measure all the way across the dish, and that's the line you're talking about. And then from that is 22 inches is the depth we're talking about. Okay, dish alignment. I did what I thought was a modern way, but I didn't know another way to get alignment on the dish. And this is something that if you take stellarium and you look at the you look at when the sun's going to be basically 180 degrees. And so you figure out the sun is at 180 degrees and what the elevation of the sun's going to be. And so what I did there was to basically align my dish to where I thought that was. And then I looked and saw where the shadow was and where I was going to have no shadow on that. And that's how I aligned the dish. So I adjusted it in azimuth and elevation to get zero shadow. And that seemed to work. It gave me, this is a 5-degree beam width dish. So it gave me pretty good, I think gave me pretty good signal or pretty good accuracy for what I was aiming it for. Any questions on that? Because that's probably the when you guys get the small dishes for the scope in the box and everything like that, azimuth was my biggest problem. On its elevation is easy. You just use I've actually got an electronic level, but azimuth was harder. I really didn't know how to do azimuth very well. I was trying to use GPS and figure out where the angle is GPS, but this was my best bet, quick to do that. Anybody else have any knowledge of how to set up the azimuth on these small dishes?
My one concern of what
Right.
you did there, Rich, was that you're trusting perpendicular of that antenna support for shadow. What we have done is tighten a rope across the whole dish vertically, and then watch the shadow go through the center. So,
oh, that's a great idea.
I don't know which
I
one's
like that.
better.
I like that. Oh yeah, I'm not saying this is as accurate. This is what I came up with to do it, but I like your idea too. And you're not relying on the. See, what he's saying basically is I've got this pole that's holding up the feed, and I'm trusting that that's actually straight. And which I just dawned on me, it may not actually be as straight as I think it is. So that putting that line across would be a very good idea. I like that.
Conveniently, we had a pedal separation right at the top and right at the bottom, so we just kind of put the the rope centered there, and
Right.
looked at the shadow coming across. We just sat there. I synchronized my phone to like GPS timing by taking a picture of the computer screen of a time, like what is it, time.info or something. And then went outside, and when it crossed, I took a picture, and then I compared the timing later to figure out is that really south. Good luck.
Yeah, great. I think
Yep.
that's but I think you guys will find that azimuth is really one of the issues on alignment. If are you really pointing at 180 or at north when you do these drift scans?
Yep. One thing I did, Rich, I have a tripod support holding up my feed, and I put a laser pointer and made sure the laser pointer was perpendicular to the feed plate, and then adjusted the tripod feed so that it was pointing directly at the center of the dish, so I knew I was vertical to the dish. And then basically did the same kind of thing you did, which gauged it by shadow. And then once I got the receiver running, then I could actually look at the bell curve as the sun passed through the dish, and knew where it should be and where it actually was, and then knew how to adjust the position to be as close to the sun passage as possible.
Right. Yeah. Great stuff. I like all that. Okay. Okay, let's look at the Spectre Cyber screen here. On the left is volts. On the bottom is kilohertz. You notice the blue is the coming toward you, and the red is going away from you. Here, what I did is I labeled you can label the target. So I labeled the target with the declination number because it doesn't record declination anywhere. And then what I did is I set it for sidereal time. So what it'll do is it'll actually record the sidereal time while it's taking data. So each scan is recording the sidereal time of that. And if you're doing a meridian drift scan, the sidereal time is your right ascension. So with this screen, I was able to label each file with the right ascension declination I was looking at, just by labeling the target with the declination number. There is a voltage. It measures in voltage. The bottom actually gives you a real-time voltage number down here on the bottom right. So I can actually tell one is, it actually tells me the data. So it says I'm getting 405 kilohertz at 3.145 volts. Now I can change the voltage settings on this thing so it doesn't saturate. The one problem I got with the current one is I got too much signal. So it only goes to 10 volts, so it'll saturate up the top, and then it'll come back when it comes down. I'll see it again, but it'll be flat on the top. So the problem with that is that you can't get the peak. You can't get the peak, and you're interested in the actual frequency the peak's at. So you need to lower this thing down so you only get the peak is within the screen, because that'll also mean that it's actually being recorded. If you have it flattened on the top, it'll just say 10 across on your data, and you don't know where. You'd have to interpolate where the actual center, where the actual peak was. And the peak is what is important here. You're after the peak of the signal, and if you got enough gain and you see multiple peaks, in fact, this is what I'll show you at the end. When I did the 60-foot dish, I actually was seeing the multiple peaks in the signal, and I had to make a decision which peak I was going to use. So I chose the left peak for all of them, just to be consistent. Here's the status, your configurations here. I do have an autosave. There used to be a noise system on this, and I think Charles knows about that better than I do. I can rescan. I can change the scan rate, so I can actually scan across this thing faster. Or I can do a slow scan rate. I can actually queue it up, so I can say only start recording at this time and stop at this time. So that's very good if you're just after a certain signal and you don't want to record all day. That'll work. You've got two modes here. You got spectrum, which is what you see now, that it's actually doing an FFT and giving you a spectrum at each frequency. Then you have continuous, which is basically going to give you overall total signal. I've had very poor luck with total signal with this system, so I've never used that successfully.
Rich, how many bins are you dealing with here as far as your FFT goes?
I think when I look at my data, I think I've got five kilohertz bins. When you actually look at the data that's in the file.
Yeah.
So basically you have to, you got here, I got a 2000 points with 5 kilohertz on each point.
Okay.
So,
I've always been wondering about the Spectra Cyber, because I think it does not do an FFT. I think it's a scanning receiver.
Okay.
Yeah. Charles, are you online? I think Charles was involved in the actual development of this. I don't know. I don't know. It's a pretty old piece of equipment. It may not do an FFT. That might be exactly right. It actually, so you're saying it just basically goes to the frequency, scans it, gets the data, goes to the next frequency.
Right.
And then, so I'm getting actual data instead of getting FFTing it. But that, I think you're exactly right on that.
Yeah,
you're right.
You could also see it when you were showing it at the very beginning. It was sort of scanning through one dot after the other. So that's very much a sign of a scanning receiver. And also, I think when the Spectra Cyber was developed at that time, you didn't have the capability on that amateur level to do an FFT.
I think you're right.
Yep. Okay.
So that's great. So we're getting we're pretty much getting straight data from each point. Okay. I could set the range for how many kilohertz plus or minus. The 0 you set in the data what the actual. So I put the hydrogen 1420.4057 megahertz. So that's 0, but there's a rest correlation there. So correction. The one thing that I would change on this, and I've done it once, but I couldn't find my my signal generator, is to get a signal generator that that you can set for the exact frequency, the center frequency, and turn it on in front of this thing and set and calibrate your 0 point. Because if the 0 point's off, all your calculations are going to be off by the same amount. So I'd recommend that, and you can use the rest correction there to actually adjust your screen and your data to the actual value. Here, I don't know that 100% that it's exactly at 0, even though I set it at that, but it just may be off by some kilohertz. Integration, I can set it for integration time, I think 1 second, and some lower integrations I can set it at. Offsets, I use this a lot. Basically, if you've got too much signal or not enough signal, you can basically subtract a voltage from the signal here, and I can lower the whole signal by a certain amount of voltage. I'm using that a lot here because I've got too much signal and it's going way to the top. So here I basically, with the offset numbers, I can actually just, before it goes to the screen or the data, I can subtract across the entire data a certain amount of voltage. And so the other interesting thing is this will not let you, if I do that, I have to restart the scans. So it won't let me, I can't do that while I'm running scans. I have to reset, and it's not a problem, but if I want to play back, then it is a problem. Let's see, IF gain. Right now I've got the IF gain set, the max is 25 dB. So I got the IF gain set way up, but just the way it works. There's also a time step that I don't use much, just leave it on the default. Okay, any questions about the screen? I can also set this thing to read in kilometers per second. Basically, I have to put my latitude, longitude in the data, and then it'll actually calculate what that is. And it'll display it on the screen, and it'll also record it in kilometers per second. But here I do all this in Excel, so I wanted to keep the sort of the raw data coming in kilohertz. Okay, shifting a little more to the galactic. What are we looking for? We're looking sort of for the rotation rate of the galaxy. If you look at, and by the way, that picture is, nobody actually took that picture. That is a simulation of what the galaxy looks like. But the sun is approximately 8.5 kiloparsecs away from the center of the galaxy. And they got different quadrants. Right now, the formulas I show you are basically only work in quadrant 1. I have been experimenting with the other quadrants, but basically, if you go in longitude, galactic longitude, 0 is pointing right toward the center of the galaxy, and 90 is pointing in the direction of movement of the sun, basically if you go left. All right, so you'll see that in the data. So basically, they've been using that quadrant to help do the galactic velocity measurements. If you look at latitude, latitude is, you got, basically the galaxy's a flat rotating frisbee with a center bulge in it, and so we're not quite exactly in this, the 0 point, of that of the frisbee there, but we're pretty close to the 0 latitude. So the goal is to look at zero latitude. If you're looking above that, you're actually aimed above the disk, and you may not get good data. So you want to look at the zero latitude, and the nomenclature is B. B equals 0 is the zero latitude in galactic coordinates. Okay, questions on galaxy coordinate system? Okay, a little complicated, but this is why we got it recording, so you can look at this again. So from a big picture is the sun is at a distance of 8.5 kiloparsecs away from the center of the galaxy, GC. RO is that 8.5 kilohertz, so that's the distance. The hydrogen source we're looking at is this S1 here. And the goal here is to determine what the 90-degree, how that's the speed of that hydrogen source is at a distance R here. And this is a 90-degree right here, okay? L is your galactic longitude, all right? And V naught is the speed of the sun around the galaxy, okay? VR is actually the measured, or the velocity, the actual velocity at that 90-degree angle. So the velocity of the hydrogen source around the radial velocity around the galaxy at the distance of R. Okay, so how does that work? Since the sun is at 8.5 kiloparsecs away from the center of the galaxy, I want that R to be as close to that, because I want to be measuring it up here so that I'm pretty close to the, where the sun is. So 90 degrees, this would be the speed the sun would be going right here, okay? And note that anywhere in between there, I actually know the speed of the galaxy at any point I want, simply by viewing the longitude at different longitude numbers. So 0 longitude is looking right at the center of the galaxy. 90-degree longitude is looking all the way to the end. And then in between that is where I'm looking for. Now you'll see this when we start looking at the entire rotation rate of the galaxy. The formula that I got from a book is this VR is the received velocity that you're measuring at a certain longitude. So the stuff I'm getting from the Spectre Cyber is this number. Okay, VR is the that velocity. So this VR is what we're after. R naught, I'm going to explain that. That's this distance. R is the is this here, and then you take the sine of the longitude. V naught is the speed here, and that's a given number. L is there, and then VLSR. I've been listening to the Wolfgang and I think it's Alex go over how do you get VLSR, and they found a nice tool for that, and I'll show you that. That really helps, because I was trying to calculate it manually. It's a pain. All right, so basically you move everything around, you get this VR minus V naught sine L plus VLSR. Note that whether this is a plus or minus was an issue with me. I had to actually guess, and I used the plus or minus based on what came out, give me the best number for what I was expecting, because I wasn't sure either add or subtract VLSR. But this is the number that worked. A plus VLSR here worked. And then you divide it by that. Okay, so here's the stuff here. Now, because this at 90 degrees is sort of the edge of where the calculations work, so I chose 85 degrees. I wanted something close, but not right at the edge of the calculation capability of this formula. So I chose 85. When you see the end of this thing, I actually chose from 0 to 90. When I use the 60-foot dish version. But here, in order to get just the rotation rate of the galaxy at pretty close to where the sun distance is, then I used 85 degrees longitude. And any questions on this whole thing? It's a little much, but it sort of explains where we're going with all this. So realize what we are measuring, this number here, VR. Everything else is a given. V naught's a given at 238 kilometers per second, and VLSR is going to be a given based on when you took the data. This is a number you have that you got to cut. There's actually an online system that tells you what the green bank VLSR is at any time. So that helps. So you don't have to calculate that. Otherwise, that's a pretty hairy number to calculate. And then down here, you know all these numbers, and then sine of L. Okay. So this is the one thing that I always have trouble with, because I don't have a ready calculator for it, is how do you change? I know I want to get the galactic coordinates. I want to be at galactic latitude 0 and galactic longitude of 85. But what is that in right ascension declination? So if you go to the I think I had the website there. This is the oh, I forget which one this is. The NASA coordinate converter. So it's a NASA Goddard website. Then you can have this, put your numbers in here in galactic coordinates, and it'll spit out your J2000 right ascension declinations. And so that's what I did. And so what you see there is the right ascension for 085 is 20 hours, 52 minutes, and then declination of 44 degrees, 35 minutes. Okay, and you can see here that the longitude L and B here is correct. So that's actually the galactic coordinates, the same thing. All right, so that is how I easily came up with the right ascension declination, and then it sort of verified it. So when you see it, I'm at 44 degrees. I tried to get a little above, but I got a 5-degree beam width, so it's very hard to get, 45 degrees or 44 degrees. So basically, 44 is as close as I can get with this, the way I've got it set up in the back. Okay, the measuring point. This is the point I actually used. It's not, you see that my current today was a lot bigger, but you basically want a well-defined point. And sometimes when I was doing the 60-foot dish, I was getting multiple points. And if you look at some of the hydrogen databases, you'll see that they actually have multiple peaks. If you have another peak there, you're possibly, what you're doing is you're looking through the galaxy, and each you have multiple hydrogen clouds along that look point you're looking at, and each of those will exhibit a different Doppler to you. So when you see multiple peaks, a couple of points are happening. One is you have potentially multiple hydrogen clouds along that line, and or you've got a like Wolfgang explained at the last art top, it's potential you got an emitter behind them, and you're actually seeing some hydrogen absorption, which make it look like you're having two peaks, but you're in reality you got one peak with an absorption cloud in between. So, but this right here appears to be no absorption cloud, but a nice, a single hydrogen cloud that's exhibiting, that's outputting hydrogen frequency and giving you a Doppler shift. So what you're looking for is a nice clean thing. If you got a hump there, you may actually have an absorption cloud in between that's giving you two peaks, but you want a nice single peak.
Richard, if I can make a quick comment on that. An absorption line would always go into the negative, and you won't to dish because the hydrogen emission is so dominating, and the continuum source is weak in comparison. That changed. So what we have seen with a 20-meter dish, I believe it was a 20-meter dish, that was an absorption line. We can see an absorption line with our 25. But what you're seeing with a 3-meter dish is all emission, and you were right. The different bumps that you see are different arms of the galaxy. They rotate at different speeds, so you see the different arms.
Yeah, and believe it, people, when I was doing this, I didn't have any astronomy background, and I'm learning so much astronomy doing this, because that's the kind of data you just need from someone who understands the astronomy part of this. This is really fun. Okay, the data comes out in basically it comes out in a string of just numbers, and those numbers are actually the voltage levels recorded. Okay, so I took the data, the file, opened it in Word, and then, or actually in Notepad, and then I embedded it into Excel, and then I had to manually stick a hertz, what the frequency is, based on going from you know, what the center frequency is, and then plus or minus 1,000 kilohertz, what the frequency change would be on each one of those. And from that, basically, you get 2 lines here, and you know, this was the peak signal here at 4 volts, and it was at this frequency there. So that's the only thing I hate about this is that doesn't actually tell you the frequency recorded it at. It just gives you a string of voltages. You know, you have X number of voltages you get, and you have to go and basically put this table together. So what I did here is I basically, you know, here's the base frequency I used, and then here's the frequency that had the highest signal level, and then I used basically this formula here to calculate what the Doppler in kilometers per second would be. So that's how you determine that, and basically you're using this number here in green is that peak there. Okay, it's easy to find. In fact, you can do a you know, find max kind of a thing in Excel, and it'll find it for you. This is and even Alex probably explained this better than me. The Earth is actually, and the Sun is actually moving toward the galactic center at a certain rate, or actually moving toward the object you're looking at a certain rate. And so you need to just count the Earth's movement and the Sun's movement toward that object or away from that object. And that's what this VLSR K is. How many kilometers per second of your measured data is actually being caused by the actual movement of the Sun-Earth combination. So you can get back to what the, you know, an absolute measure. So this is the number I came up with for that time period, looking at the right ascension declination I was looking at, and I came up with this number here of minus 28.975. Now this is actually for the Green Bank Observatory. I'd like to find a better way to come up with this for my current location, but this is a rough approximation of what my current position would be.
I have a URL for that allows you to put in your location.
Oh, you can put that in chat, please, and we'd all thank you for it.
I don't know if I know how to do that.
All right.
Let me
But
see.
you could also read in the Zara journal, where I posted a link to how to calculate that.
Okay, great. Yeah, this is the new stuff that you know, even though I'm briefing this to you guys, that I learned just by redoing it. I did this like 2 years ago, and then now redoing it, I realized that I didn't know as much as I thought I knew back then. So that's my continual learning curve. But this is an important number to get you to more of an absolute value on your reading there. Okay, so going back to the original geometry slide, just going down here and plugging all those numbers in, I get with a minus 221.7 kilometers per second for the velocity at, actually, if you look at this thing, it's more up here along that line. And so that's the velocity we get. Okay, so one is that's the velocity, minus 221.7 kilometers per second is the velocity of the sun around, it's actually the velocity of the hydrogen cloud we're measuring around the galactic center, which happens to be approximately our distance, actually at 8.47 kiloparsecs away from the galactic center, while the sun's at 8.5. So that whole band of material is rotating about 221.7 kilometers per second around the galactic center, which is pretty cool, just to note that. Okay, now, how do you get the mass? Well, there's a nice formula here that the mass of an object is the velocity squared times the distance over the gravitational constant. So if you take that, and I got all the numbers here, here's your distance, 8.5 kiloparsecs, times the conversion from kiloparsecs to meters over the galactic, or the gravitational constant, and I end up with about 1.94 times 10 to the 41 kilograms. Divide that by the how many kilograms of mass of suns, and you get 0.97 times 10 to the 11th mass of suns. All right. You go to the books. One of the books I have says that the mass of the galaxy is 1 times 10 to the 11th times the mass of the sun over the distance you are away from the center of the galaxy to the distance 8.5 kiloparsecs. And it comes up with the fact that we're actually measuring it at 8.47 and R, that the value I should be getting is 0.99 times 10 to the 11th mass of suns. So this approach got me 0.02 times 10 to the 11th mass of suns accuracy. I'm not sure it's how accurate, but it gave me in a very good ballpark for doing a backyard dish. Any questions on this? You now know the rotation rate of the galaxy, and you know the mass of the galaxy with using just one measurement of hydrogen.
Wouldn't the difference in your measurement versus what the book says be due to your significant figures of 8.5 kiloparsecs?
Don't get me started on significant figures. Yeah, I'm not looking at the exact point in the sky. I've got a 5-degree beam. There's all sorts of errors in here based on the equipment I'm using. And this is just the raw data I'm plugging out to you guys. I'm not, I'm not manipulating. I'm just putting this out. So it just says that there's not a lot of variability, even though you're using equipment that's 5-degree beam width, and you're basically, you're just coming up with a homemade home spectrocyber, things like that. You can do these kind of measurements to a certain amount of accuracy, and I'd like to take credit for the accuracy here, but it's just I'm thinking it's more luck. Nah, it's not luck. I've done this twice and it's come up with about the same accuracy.
Rich.
So you guys should be able to do this. Yeah.
You need to check your calculation on the Doppler shift. I went through this several times. The denominator should be the measured frequency rather than the reference frequency. Go back and look.
Okay. Okay, let me get back to you on that.
Yeah.
Okay. All right. All right. So anyway, so those are the numbers. And this is what I did in 2018. And you see the differences in you can tell this is with a 60-foot dish. I did use the SpectraCyber. We did have a cavity filler plugged in between them. But for the galactic longitude 0, and I did 10-degree differences, I just started to do 5 degrees after a while. But you start seeing two different peaks here, multiple different peaks. And those are, I'm attributing to different hydrogen clouds that I'm looking at. So you have to sort of make a decision. So I made a decision to use the left peak on anything I had more than one peak on. And same here. And this is actually what the 085 looked like there. So you see sort of a couple peaks on mine with this, but see how significant mine, they look like almost RFI there, but those little bumps I've got on my signal are actual big bumps when you look at them with a 60-foot dish. So that's sort of the difference in quality, I think you could see, in definition with the big dishes. So if you do this for every, R value that you're looking at, you see a plot like this, where this is your kilometers per second. And then you see when it gets up to about 4 kiloparsecs away, it flattens out, okay? If you had a real spiral galaxy that it would not flatten out, it should increase, I believe. This is actually this plot. By doing this plot, this is how they came up with dark matter. That in order for it to flatten out like this, the galaxy had to have more mass than what they were actually seeing. So this plot here, if you just do it at different galactic longitudes and do the same calculation I just showed you for velocity at the different R points, then you should see something very similar to this based on your setup. And you basically, this is the entire galactic rotation rate of the galaxy. And if you'd have done this back in the past and you knew what you're doing, you could actually have claimed that you've figured out dark matter, that dark matter had to be involved. So that's also, I thought, very cool. Do that. Okay, any questions on how you get this plot from, notice that the 8 right about here is where I give you one data point. But since it's flat almost to, between 4 and 8.5, it didn't matter. Theoretically, I could have taken any of these points and you'd have still got pretty close to the same value. Okay. Any questions?
A comment from my side, Rich.
Yeah.
In order to determine the velocity, you have taken the peak of the spectrum, the left SpectraCyber plot. What you're using is the tangent point method, and what you should actually do is not take the peak, but the let's say the leftmost appearance of any hydrogen signal.
Okay.
That has to do with the fact that you're looking at a tangent point, and you really want to be exactly at the tangent point. That's especially in the area where you're closer to the galactic center, that is lower galactic longitude, you will see some weaker signals that extend out. And what will then happen is that you actually see that the rotation velocity of the Milky Way increases rapidly and then decreases a bit and then goes into this parallel, almost constant thing. So that's exactly the same. You will get the same result for the larger distance from the galactic center, but it will give you a somewhat different view of when you're close to the galactic center. Okay.
I think I did that on this one here because, for example, I chose that one instead of that one. So
you would actually go further to the left, really where the peak starts, not on on the maximum of the peak, but where the peak starts.
Oh,
At the
really?
base of the mountain.
Yeah, I know that
Oh, wow. Okay.
where people, I've seen wrong descriptions of this tangent point method where they say you should take the peak. That's not correct. You should take really the fastest hydrogen that you can see, fastest in the sense of redshifted. The most redshifted hydrogen that you can actually detect somewhere in your spectrum. That's the point where you want to be looking at.
So Wolfgang, that's whenever it starts to come up from the baseline. Is that the?
Yeah, that's
like
when it
right
starts
there?
to come up from the baseline. Of course, there's a bit of interpretation, and also depends on the signal to noise. There's some uncertainty into that, but that's the idea, that you take the fastest redshifted hydrogen signal that you get.
Nice. Thank you. Yeah, they don't, the little galactic book I had didn't explain any of this. Okay. All right. Any more questions on the galactic rotation rate? So I believe, let's just take for an exercise for everybody who's got their hydrogen data. If you now go do you follow these directions, and supplemented by all the stuff that Wolfgang and everybody else has commented on, you should be able to get this kind of a plot. You should be able to do the calculations, and you should be able to basically reproduce the galactic rotation rate. All right, and that's I think is an exercise for Sarah. That's very good stuff. You can brief that to science people, and you actually eventually might come up with something good. Now, the other thing I use the data for, this is definitely the starter kit. If you want to learn the better stuff, you talk to a couple other members who can actually take the data and make beautiful plots out of it. But this is what I did in the early days, where I've got right ascension declination, and I took the peak signal strength, and basically I stuck it in each one of the blocks for right ascension declination. Very time consuming, painful process, but since I collected all the data, I just did it. And you can see how nicely the hydrogen signal strength is on this plot from right ascension declination. So that's something you could do there, and there's a number of other ways to do it with Python and things like that just sucks the data in. So the last plot I want to show you is this, but using galactic coordinates. Galactic coordinates, you notice at the 0 point, and we measured it all at 0 galactic latitude. But the galactic, we measured it at different right ascension declinations when I did the drift scan. And that drift scan is associated with different galactic latitudes and longitudes. But this is what it plots like across the entire sky. And believe it or not, this is southern hemisphere, this area right here. So you get a nice galactic plot. When you do a full drift scan, that's everything. That's just not galactic, your 0 latitude, galactic latitude, and longitude. This is the entire sky from vantage point of my backyard. And then plotting it, you see how the hydrogen is right across the center of the galaxy, is where most of it is. And then you get those big, obviously gaps here because there's southern hemisphere shows up right about here. Okay, let's see. A number of you guys have the ability to suck the data in and convert that to Python. You want to go over those? No? Okay. Am I still online? Yep. Ted, you want to go over your how you can do that?
I'm tempted, but it's just not ready, guys.
All
We're
right.
getting closer and closer. I am eager to present it upon the world, but only to limited parties at this point who are very forgiving.
Well,
let me give a little advance notice. Ted has taken my data and been able to make beautiful plots automatically, sucking the data in and then outputting it without manually embedding each one of these numbers into the plot like I just did in Excel. And it's come out beautifully. All right, so I know he doesn't, but the goal here is eventually we get you be able to take your data and take a Python program and have it suck in all your data automatically and then plot it out, which takes a lot of the mechanics away from doing this and makes you have almost real-time plotting capability of the data you're getting, which is going to be really nice, especially with all this hydrogen data we're getting. And then you can combine other people's data as long as you've got it calibrated in right ascension, declination, and time, and get and add that data to combine that data. And so we should be able to get combine a 60-foot dish with a 3-meter dish, and see how that all works. So we have a lot of opportunities here in the future here. Okay, some things I'd like to improve. I want to calibrate the base frequency. As I'm saying, I'm not 100% sure that when this thing reads 0 point that's actually the frequency. It's not plus or minus some kilohertz. VLSR, hopefully someone puts that in the chat, that VLSR measurement, especially at location here instead of just green bank. 9-foot dish pointing. I got a 5-degree beam, but I'd still like to get as close as I can with that. And different galactic longitudes. It'd be nice if we automate this a little bit. I can get, maybe 1 degree galactic longitudes all the way up to 90 instead of that, of just doing the 90 point. Okay, there's lots of other improvements to make on this. I guess the next thing I'm going to do with this approach is to take the scope in the box SDR and just plug it into the dish instead of the SpectraCyber and see if I can reproduce this thing with the SDR. I think it outputs the same kind of a serial file, and so it should come out pretty close, and we'll just see if it works. Okay. All right, so that's all I've got. Any questions?
Rich, on your dish, the setup is that it is looking due south and stationary, and you can change the elevation. Is that correct?
Right. I do have an actuator on there that allows me to change that. I have to turn it all the way around to do north meridian. So I go to 0 to 90 degrees, and then I have to turn it around. And I can go 90 degrees elevation down to 0 again on the other side. So right now I've got it actually pointed north because I'm at 44 degrees, and I'm only 38 degrees latitude. So I had to change it to the north meridian, look at north meridian a little bit for these measurements. I do have an actuator that I can actually move that from here. Okay.
Rich, you set your PC to sidereal time. Is that a constant for all days of the year, or what?
In the software, the SpectraCyber software, it has you put in your latitude and longitude, which will automatically calculate sidereal time in the software, and then actually record it in sidereal time.
So that's what it sends out the serial port.
Yeah, that's actually it's recording it versus the time stamp that's on each piece of data is sidereal time. Which if you got it in north-south, if you're north-south meridian, that is right ascension.
And that would be constant for your location all through the year, correct? So we could convert it back to UTC pretty easily.
Well, it changes by 4 minutes every day. So the difference between, let's say, the UTC or for that and the sidereal time, there's a 4-minute difference per year. That's why, because of the rotation of the Earth around the sun. So it does change.
So we have to do math with the date and the sidereal time to get back to UTC. Is that correct?
Well, I've got on the top, it says when the scan was taken in UTC time. All right, that is the top label that is put on each file. Each individual line item had what? Let's see. Yeah, that also has, it has the UTC date and it has sidereal time. I'm sorry, it does not have UTC time because I could set it for that, but what I cared about was right ascension.
I understand.
Now, all
There's
you
a
care
convenient
about,
way to record RA.
yeah, you don't care. You will know based on the timestamp on the file what the actual time was, but all you care about is the right ascension declination, and combine it with the same right ascension declination someone else took, no matter what date it was. Does that make sense?
So as we copy your file around, we have to be careful to record the original time of the file, though. That's my concern.
I don't think so. All you care about is the right ascension declination. Need to know approximately what date it was taken, but and the location it was taken at. So yeah, I guess we're going to have to add some more sort of quote metadata on there, because you need to know that to help your VLSR data. And
Well, as long as we can convert back. Okay, I'm going to run my program on your old data and see what happens.
Oh, great. Great, love to see it. Okay.
Question on the, hi, this is Anthony. Question on the Spectre Cyber hardware and software. Does it support multiple receivers and multiple antenna feeds, or is it just one antenna feed and one LNA?
Well, it has a down converter. It down converts to IF. It has its own receiver, and so my belief is it'll handle 1420 megahertz feeds from any source coming into the back with one input, and then it'll do the scan across there. That help?
Yeah, I think I get what you're saying. I'm just kind of curious if you wanted to feed multiple antennas, but I guess you're telling me with the megahertz, it would support that more than one antenna source.
Okay, so it only handles one antenna source at a time. Okay. That's what I'm saying. If I wanted to do multiple polarizations, it would not handle that because it doesn't have two inputs that would then combine it.
Gotcha.
So that's yeah. All right. Any other questions?
So I have some comments to make.
Sure.
A couple of thoughts I have. So you said about this project, and you got your telescope going, and you collected all this data, and then you did the calculations, and you proved to yourself that you matched the numbers that you've seen other people publish on velocity and mass, and that all feels good. And then you think, what else could I do going forward? And if you were a scientist, maybe somebody might say a project could be to do this on a regular basis and try to be really methodical about how you're doing it so that you're repeating the measurement accurately from one time to the next. And then you could potentially monitor the change in velocity of the galaxy or the change in mass of the galaxy and get data on that. And that could be very interesting also.
Oh, I agree 100%. I mean, until you get a baseline that you can actually prove that your system's working and it's getting reasonable data, you've definitely not improved everything. In fact, there's so many improvements I need to make on this, and even getting rid of the Spectre Cyber, even getting off the 9-foot dish and doing it with a different dish. There's all sorts of many things that now that I have this competency level at a very basic raw values, that I now can jump to more precise, more better stuff. I think that's where exactly what you said is that this is the start of my learning curve. The fact that I got something working. If I didn't get this thing working, I may have quit a long time ago. That I didn't have this data, because it's just, if I can't actually get real data, The other thing I think that a lot of the guys in my group who are engineers fell sort of in the trap of they sort of quit as soon as they got the data because the system worked, and then they sort of lost focus in that. Well, let's go. Well, they didn't lose focus. They went from hydrogen to pulsars, and they started working on pulsars because the hydrogen solution was solved. Now let Rich go collect data all he wants, but we don't want to collect data. We want to go build something different. And that's sort of the focus you lose from the technician engineering side to the science side, is that the engineers want to build something new and the science guys want to take data. So that's the way I'm sort of seeing things work.
Yeah, I agree totally. And sometimes when you do something, you sort of reach this proof of concept and you think, let me go to the next thing. I agree. On your timing thing, I was going to make a comment about that too, from an engineering point of view. Whenever we measured the speed of something or the rise, you usually would measure rise time of a signal. You'd measure it from the 10% to the 90% point. And so we set it up on an oscilloscope. And the oscilloscope's got dotted lines that have been put there in the past for that purpose to help you find the rise time of something. I'm wondering if the 10% point could be a good reference point to decide that, hey, the signal, this is the beginning of the signal within a certain point. Because if you start trying to pick that beginning time, it's going to become if you don't have some method that you're using, it's going to become some variation in your measurements, I'm thinking.
Yeah, I think that you're right. I think it's just a question of where is the data point that is the best. I think with Wolfgang, that's new information that Wolfgang gave me, that the actual best might be at the base of the data from the baseline.
Yeah, I think the point that Bob was making, that we could take a 10%. So where's a 10% increase? There's still some uncertainty because that might be hidden in noise or might not be hidden in noise. It's depending on the signal to noise ratio that you have. But anyway, I mean, taking 10% is a good starting point.
Just might be but more consistent, more accurate than either taking the base or taking the peak. Is that what you're saying? Yeah.
Yeah, I mean, I said that you should take the point where the signal starts to be visible. Now, obviously, there has to be some decision made. Is that already okay, or is it still in the noise? And if you take as a good measure 10% of the maximum signal, that's, I think, is a good starting point. While I'm at it, just a quick comment on another comment that Bob did. Doing these experiments over time and see changes, I don't think we will be living long enough to see any changes. This has to do with the rotation of the galaxy. That's of course it changes, but it's so slow that I'm afraid we won't see it. There are other effects, obviously, where you see rapid changes, where it is of great benefit doing the experiment over and over again. But the hydrogen line in our galaxy is not changing that rapidly.
During the briefing, many of the members added in chat various links to tools and procedures that help the conversation. This completes Sarah's presentation of a radio telescope observation party for this month. If you're interested in amateur radio astronomy, please visit our website at radio-astronomy.org. Thank you.